Hello, this video is about simple harmonic motion. And before I talk in detail on what the definition of simple harmonic motion is, I would first like to talk about motion of a spring. Motion of a spring is governed by Hooke's law. And Hooke's law states that the force of the spring equals to negative kx. What I mean by that is if there is a spring, then the spring is at an equilibrium position x naught. And if the spring is stretched such that the distance stretched equals to x, then the force exerted from the spring equals to negative kx. There is the negative sign in this force law because the force from the spring is pulling the mass towards the equilibrium position. Therefore, there should be a negative sign in the force law. And we also see that the magnitude of the force is proportional to the distance stretched, which seems like a likely behavior of a spring. From Newton's law, force equals to ma, therefore ma equals to negative kx. And solving for a, acceleration, which is d2x over dt squared, equals to negative k over mx. Now note that this is a second order differential equation because this is a second time derivative of x. So since there is no formal method of solving this kind of equation, we're going to guess a solution. And my first guess is that x of t is going to be x naught times cosine omega t. If I take a derivative of x, then this is negative omega times x naught sine omega t. And the second derivative is going to be negative omega squared x naught cosine omega t. And since x naught cosine omega t was x of t, this equals to negative omega squared x of t. Therefore, d2x dt squared equals to negative omega squared x. And from Hooke's law, this should equal to negative k over mx. Therefore, if omega equals to k over m, then x of t equals to x naught cosine omega t satisfies the differential equation. Now similarly, x of t equals to x naught sine omega t also satisfies the equation, which means x of t equals to a cosine omega t plus b sine omega t would be the general solution that satisfies the motion of a spring. Now since this linear combination of cosine and sine looks a bit complicated, physicists had generalized that x of t is in the form of x naught times cosine of omega t plus some angle phi, because cosine omega t plus phi from trig identities equals to cosine omega t cosine phi minus sine omega t times sine phi, in which this becomes x naught times cosine phi times cosine omega t plus negative x naught times sine phi times sine omega t, which this is in the form of a cosine omega t plus b sine omega t. Therefore, a general solution would be x of t equals to x naught times cosine of omega t plus phi. Now, one might wonder, why would this value of square root of k over m would be used by a symbol omega, which was angular velocity? If you look at a polar function, where this polar function is r equals to x naught, if a particle moves at constant angular velocity at omega, at this position where time t has passed, on the x-coordinate, the position of this particle equals to x naught times cosine omega t. And physicists said since the motion of a spring is equivalent to a particle moving in a circle with uniform angular velocity, physicists has claimed that this quantity of square root of k over m is technically an angular velocity of this particle. Now, because of the motion around the spring, the time it takes for this particle to go around this circle, or the period of the motion, equals to 2 pi over omega. In this case, this equals to 2 pi times square root over m over k. Conversely speaking, frequency, which is 1 over period, would be omega over 2 pi, which is 1 over 2 pi times square root of k over m. Now, what if there is a mass attached to a spring with spring constant K with equilibrium x naught that has been applied with a constant force F naught? In this case, the new equilibrium position, in which the length of extension is equal to x eq, is going to be defined such that the net force equal to 0. Therefore, K times x equilibrium must equal to F naught, and x equilibrium equals to F naught over K. If I use Newton's law, the net force, which is force from the spring plus F naught, should equal to ma, or m times d2x dt squared. And since the force from the spring constant equals to negative kx, this equals negative kx plus F naught. And factoring out the k, this becomes minus k times x minus F naught over k. And since F naught over k is defined as x equilibrium, this equals to negative k times x minus x equilibrium. So therefore, the overall equation of motion equals d2x dt squared equals to negative k over m times x minus x equilibrium. Note that this looks very similar to the equation that we solved previously, which was d2x dt squared equals to negative k over mx. But in this case, x equilibrium is a constant, which means we can simply claim that x of t equals to x naught cosine omega t plus phi, which was the general solution, and simply add x equilibrium. Because in this solution, if I subtract x by x equilibrium, this is simply x naught cosine omega t plus phi. So for example, if an object m is attached by a spring with spring constant k vertically, then there is going to be the force of gravity, which equals to mg. If I set the coordinate system such that the y coordinate face downward, then the force of gravity equals to mg, and force from the spring equals to negative ky. And since x of t was in the form of x naught cosine omega t plus phi times x equilibrium, similarly, y of t is going to be y naught times cosine omega t plus phi times y equilibrium. And in this case, y equilibrium would equal to mg over k, because at y equals y equilibrium, the net force must equal to 0, therefore k times y equilibrium must equal to mg. Now, springs can be connected in either series or parallel. If two springs are connected in series, this means there is a spring with spring constant K1 and there is spring with spring constant K2. If an object with mass m is attached, now if this spring is stretched such that the first is going to stretch by distance delta x1 and the second spring is going to stretch by distance delta x2, then the effective spring constant is defined by force divided by delta x1 plus delta x2, which is force divided by the total length that has been extended. Now, since these two springs are connected, the force of the spring is effectively the force of tension, which means that the force that is applied by the spring to this object should equal to the force that is applied from the first spring, and this should be equal to the force that is applied by the second string. Also, delta x1 plus delta x2 should equal to delta x total, because the length extended by the first spring and the length extended by the second string should add up to the total length that has been extended. Because F1 is defined by K1 times delta x1 and F2 equals to K2 times delta x2, if I solve for x1 and x2 and plug into this value, I get F1 over K1 plus F2 over K2 equals to Fs divided by K effective. Now I can cancel all these three values and get the conclusion that 1 over the effective spring constant equals to 1 over K1 plus 1 over K2. And in general, 1 over K effective is the summation of 1 over all the other spring constants. So for example, if I have a spring with spring constant K naught and connect it with another spring with spring constant K naught, then 1 over K effective equals to 2 over K naught, which means K effective is 1/2 of k naught, which means the strength of the spring has reduced to half. Now, spring can be connected in parallel, which means a spring with string constant k1 and k2 can be attached simultaneously to this object with mass m. If this object is extended by distance delta x, then there is going to be force that is added from the first spring and the force that is added from the second string. And the net force is simply the summation of these two forces, because unlike the series connection, these are connected in parallel, which means the force is additive instead of being the same. Therefore, K effective times delta x equals to K1 times delta x plus K2 times delta x. And crossing off the delta x, I get K effective equals to K1 plus K2. And in general, the effective spring constant for parallel connection is simply the summation of all the other spring constants. Consider this example. Although this connection looks like a series connection, this is more closer to a parallel connection. And the reason that this is more closer to a parallel connection is that if this has been displaced by distance delta x, then the force that is exerted from this first spring is exerted that way, because the first spring has been extended and therefore the force of spring would be exerted towards the opposite direction. And the force from the second spring is going to also exert on the same direction because the second spring has been compressed, therefore it is going to exert the force outward. Therefore, the net force is equal to F1 plus F2. And since for both spring the length of extension equals delta x, this equals to K1 delta x plus K2 delta x, and therefore similar to the parallel connection, K effective is K1 plus K2. Now the force from the spring is conservative. And what this means is that there is a potential energy in which the definition of potential energy was negative integral of the force dx, and in this case this equals negative integral of minus kx dx, in which 1/2 kx squared, this would be the function of potential energy of a spring. So for example, let's say there is a spring at the equilibrium position, and the spring has been extended to length L and has been released. And when it reaches the equilibrium position, this is moving at speed v0. Then the energy when this is extended equals to 1/2 kl squared, because initially there is no velocity, so only energy that is present is the potential energy. And when this passes the equilibrium length, the energy is simply 1/2 mv0 squared, because the length of extension is 0 and there is no potential energy from the spring. Therefore, from conservation of energy, 1/2 mv0 squared equals to 1/2 kl squared. And solving for v, I get v0 equals to L times square root of k over m. And note that k over m was equal to omega, in which this equals to L times omega. Now, the mathematical definition of simple harmonic motion is that the second derivative with respect to a position variable is equal to negative omega squared times x. Now, note that this x can be distance or angle, but any mathematical variable that satisfies this equation will be considered as simple harmonic motion. Now, let's look at the example of pendulum. If there is a massless rod of length L, and at the end there is an object with mass m that is attached, and it is at an initial position where the angle is at theta naught, then the weight of this object will exert a torque on the pendulum. And torque, which is R cross F, equals to negative L mg sine theta. And note that there is a negative sign here because the torque is exerted to reduce theta. This is similar to how for a force of spring, the force of the spring equals to negative kx, because this is exerted to reduce the value of x. Now, remember from Taylor series that if theta was small, then sine of theta can be approximated as theta. Therefore, torque can be approximated as negative L mg theta. Now, since torque equals to inertia times alpha, inertia in this case is simply ml squared, and alpha is d2 theta over dt squared. Therefore, ml squared times d2 theta over dt squared equals a negative L mg theta. Crossing off the L and the m and dividing the length, I get d2 theta over dt squared equals negative g over L theta. And we see that this looks very similar to the differential equation from the spring, which was d2x over dt squared equals to negative k over mx. So therefore, theta of t is going to be theta naught times cosine omega t plus phi, where omega equals the square root of g over L. Just like how x of t equals to x naught times cosine of omega t plus phi. Now, since omega equals the square root of g over L, the period of the motion, which equals to 2 pi over omega, equals to 2 pi over square root of L over g. And from here, we note that the period is not dependent on the mass, but it is only dependent on the length and the gravitational acceleration. Similarly, for the period for the spring, this equals the square root 2 pi times square root of m over k, in which the length of the extension, the length of the stretch, does not affect the period of the motion, which means if this spring is stretched by a distance a, and if the spring is stretched by a distance 2a, for both of these two springs, the period of oscillation is going to be the same. Now consider this example. A pendulum is raised up to an angle theta naught. Since the force gravity is conservative, the energy of this mass pendulum system is conserved. When this is raised at angle theta, then the height that is raised equals L minus L cosine theta, because the length of the rod equals L, and the length from this end to the object equals to L times cosine theta from trig identities. Therefore, the potential energy equals to mg L times 1 minus cosine theta naught. But when this pendulum is released and reaches at an angle theta equals 0, the gravitational potential energy is 0, but the kinetic energy equals to 1/2 mv naught squared. And from conservation of energy, 1/2 mv naught squared should equal to mgl times 1 minus cosine theta naught. Crossing out the m and solving for v, I get v naught equals to square root of 2gl times 1 minus cosine theta naught. Now I've prepared several questions from the recent F equals ma exam related to oscillation in simple harmonic motion. And the first one's from year 2016, question 14 and 15. These two questions are related. So in this question, a rod of length small l is fixed by a pivot. And at the end, there is a spring of length big L that is again fixed by a post, where the length of the spring is far greater than length of the rod. Then calculating the frequency of this system, if this rod is displaced by an angle theta, then change in L is roughly L times theta, as the change in length can be approximated as the arc length with radius L and angle theta. Therefore, the force that is applied by the spring equals to KL theta. Now, calculating the torque that is exerted by this force. Torque equals to negative L times KL theta, where this is the force and that is the distance from the pivot. And since big L is much greater than small l, the angle in between the force and the displacement can be approximated as 90 degrees. So therefore, torque equals to negative KL squared theta, which should equal to I alpha. Therefore, alpha should be negative KL squared theta over I. And since this object is a rod at the endpoint, the inertia of this object equals to 1/3 ml squared, which this became, in which angular acceleration equals to negative 3k over m theta. Therefore, frequency, which equals to 1 over 2 pi times angular frequency equals to 1 over 2 pi square root of 3k over m. In question 14, this spring is placed at the midpoint of this rod. And when this rod is displaced by an angle theta, using similar logic, change in L is roughly L over 2 times theta. Therefore, the force exerted equals to K L over 2 times theta. And since the force that is exerted and the displacement are roughly vertical to each other, the torque that is exerted by this force equals to negative KL squared over 4 times theta. Note that this is KL over 4 because force equals to KL over 2 times theta and the displacement equals to L over 2. Now, since torque equals to I alpha, the angular acceleration equals to torque, which is negative KL squared over 4 theta, divided by inertia, which should be 1/3 ml squared, since the fact that this object is a rod have not changed. Solving for this, I get angular acceleration alpha as 3k over 4m theta. Therefore, frequency, which is 1 over 2 pi omega, equals to 1 over 2 pi square root of 3k over 4m, which is exactly half of 1 over 2 pi times 3k over m, in which this was the original frequency that we calculated previously. Therefore, for question 14, we proved that the frequency is reduced to half. Now, question 15 is similar to question 14, but instead this case, the spring is connected horizontally instead of vertically. And the spring has been already extended by distance L. If the rod is displaced by angle theta, then the length stretched from this twist of the rod is negligible. Therefore, we can claim that the change in L is simply L. And therefore, the force applied by the spring equals to KL. But since the length of the spring is far greater than length of the rod, we can assume that the force of the spring is exerted horizontally, and therefore the torque that is applied to this rod equals to the force times L times sine theta, which is approximately KL squared theta, because sine theta can be approximated as theta, and force is simply KL. Now, using torque equals to I alpha, alpha equals to torque divided by inertia, in this case equals to KL squared over theta divided by 1/3 ml squared, since this is a rod at the end point. Canceling out the L squared, this becomes 3k over m theta, and therefore frequency, which should be 1 over 2 pi times angular frequency, equals to 1 over 2 pi square root of 3k over m, in which this was the value that I got on the original situation. Therefore, for question 15, the frequency have not changed. The next question is question 7 from 2016 F equals MA exam. In this question, there is a mass that is connected by two springs of length L. And if this mass is stretched by a perpendicular distance A, the question is asking what would happen to the period of the motion. Change in x for the spring equals the square root of L squared plus A squared minus L, because initially the equilibrium length was L, and this has been stretched to a length of square root of L squared plus A squared, which means the force from the spring equals to negative K times square root of L squared plus A squared minus L. Drawing the force vectors, the two force vectors would add up such that the horizontal component would cancel out and only the vertical component would remain. So therefore, the net force would equal to 2 times force from the spring times sine theta, where theta is this angle. And expanding this term, this equals to negative 2 times k times square root of L squared plus A squared minus L times A over square root of L squared plus A squared, in which this equals to, if I bring in 1 divided by L squared plus A squared inside here, this becomes negative 2k times 1 minus L over square root of L squared plus A squared times A. Note that if A is far greater than L, then L over square root of L squared plus A squared is just going to go to 0. Therefore, the net force would equal to negative 2ka, in which this would be a simple harmonic motion. Therefore, T would be constant when A is far greater than L. But if A is far less than L, then L over square root of L squared plus A squared can be expressed as 1 over square root of 1 plus A over L squared, which is in the form of 1 plus A squared over L squared to the power of negative 1/2. But from Taylor series, 1 plus x to the nth power can be approximated as 1 plus nx as long as x is extremely small. Therefore, L over square root of L squared plus A squared can be approximated as 1 minus A squared over 2L squared, because in this case the exponent equals to negative 1/2. Plugging in this value to the force equation, I get the net force equals to negative 2k times 1 minus 1 plus A squared over 2L squared times A, in which this equals to negative k A squared over L squared times A. Now, if I approximate this net force as a simple harmonic equation such that the net force is in the form of negative omega squared A, omega would equal to A over L times square root of k, which means period equal to 2 pi over omega would be 2 pi over square root of k times L over A. And from this equation, we see that the period is inversely proportional to A. And therefore, the correct answer would be answer choice C, where T would decrease as A increases and T reaches a value of constant period. Next question is question 23, and this is one of those questions where you have to split those masses into an infinitesimal mass and use Newton's law in order to solve it. So in this question, there is a rubber band of mass m and radius r. And when this is rotated at angular speed omega, the radius has increased by an increment delta r. Then the question is asking, what is this new radius of the rubber band? Tension that is applied by this rubber band can be approximated as k times delta L from Hooke's law. And change in length is simply 2 pi delta r, because originally the circumference was 2 pi r and the circumference has increased to 2 pi times r plus delta r. Now, if I take an infinitesimal mass at the edge of the rubber band where angle is delta theta, then tension is applied at both ends. And using trigonometry, the component of this tension along the radial direction is equal to t times sine of delta theta over 2. Therefore, the total force on the radial direction equals to 2 times t times sine of delta theta over 2. And since delta theta is really small, this can be approximated as 2 times t times delta theta over 2, which equals to t times delta theta. Now, the force along the radial direction must equal to the centripetal force, which means tension times delta theta should equal to the delta m, which is the small mass, times v squared over r plus delta r. Now, but since v equals to r plus delta r times omega, this expression can be rewritten as delta m times r plus delta r times omega squared. Now, delta m in this expression can be expressed as big M over 2 pi divided by delta theta, because mass is proportional to the angle, and the mass angle density, or mass divided by the total angle, equals to m divided by 2 pi. And therefore, solving this expression, t was equal to k times 2 pi times delta r, and delta m was m divided by 2 pi times delta theta times r plus delta r omega squared. Canceling out the delta theta, and multiplying out the 2 pi, I get 4 pi squared k delta r equals to m times big R plus delta r omega squared, which equals to mr omega squared plus m delta r omega squared. If I move this term to the left, I get 4 pi squared k minus m omega squared delta r equals to mr omega squared. Therefore, delta r equals to mr omega squared over 4 pi squared 4 pi squared k minus m omega squared. Therefore, the radius, which equals to r plus delta r, equals to r plus mr omega squared over 4 pi squared k minus m omega squared, which equals to 4 pi squared k minus m omega squared over 4 pi squared k r minus mr omega squared plus mr omega squared. This term cancels out, in which the new radius of this rubber band is 4 pi squared k r divided by 4 pi squared k minus m omega squared. The next question is from 2017 F equals MA, question number 2. In this question, there is a box with mass m, and inside this box, there is a spring with spring constant k that is connected to an object of mass small m. If this box is held stationary, then the situation is equivalent to this object, mass m, hanging on a ceiling with spring constant k. In this case, the angular frequency omega equals to k over m. However, if the box is under free fall, then the situation is equivalent to the two masses, big M and small m, that is connected to a spring that oscillates together. And the oscillation of the two masses can be thought as, with respect to the center of mass of those two objects, mass big M and mass small m oscillates at the same frequency omega prime. If I call the spring constant of the bottom half as k1 and the spring of the top half as k2, then omega prime equals to square root of k1 over small m, which also should equal to k2 over big M, since the frequency of the both mass should be the same. Therefore, k1 over small m equals to k2 over big M. But since spring 1 and 2 are connected in series to make a spring with effective spring constant of k, 1 over k equals to 1 over k1 plus 1 over k2. But from this expression, k2 equals to big M over small m k1. Therefore, 1 over k equals to 1 over k1 plus big M plus small m over big M times k1, which equals to m plus big M over m k1. Now, therefore, k1 equals to small m plus big M over big M times k, which is greater than k. Therefore, omega prime, which equals the square root of k1 over m, is greater than k over m, which equals to omega. And therefore, when the box is under free fall, the angular frequency increases. The next question is question 24. In this problem, there is a mass of small m traveling at speed v, and at the other end, there is a mass of big M attached to a spring with spring constant k. If these two masses collide elastically, then the question is asking, what is the maximum compression of the spring? Now, in order for the spring to have maximum compression, then the two masses, m and m, are traveling at the same speed. And this is because when small m and big M are traveling at the same speed, the change in length with respect to time is going to be 0, which means the total length of compression is going to be at its maximum. Since the external force equal to 0, the momentum is conserved. Therefore, mv equals to m plus big M times v final, where v final is the speed of those two masses traveling at the same speed. Solving for v final equals to mv divided by m plus big M. Since no energy is lost, I can use conservation of energy as well. Initially, this mass only has kinetic energy, so initial energy equals to 1/2 mv squared. And final energy equals to 1/2 m plus big M v final squared plus 1/2 kx squared, because the mass of small m and big M are traveling at the same speed of v final and therefore have kinetic energy of 1/2 m plus big M v final squared. And since the spring is compressed by distance x, it has a spring potential energy of 1/2 kx squared. And since energy is conserved, 1/2 mv squared equals to 1/2 m plus big M v final squared plus 1/2 kx squared. And plugging in the value of v final to here, I get 1/2 m plus big M times m squared v squared over m plus big M squared plus 1/2 kx squared. Canceling out the mass term and moving this term to the left, I get 1/2 mv squared minus 1/2 m squared v squared over m plus big M equals 1/2 kx squared. Canceling off the 1/2 and factoring out the mv squared here, I get mv squared times 1 minus m over m minus big M equals to kx squared. And therefore, kx squared equals to mv squared times big M over m plus m. And solving for x equals to v times square root of m times big M over m plus big M times k. The next question is from 2018A F equals ma, question 11. In this problem, there is a mass that is attached to a spring, and I'm going to call this spring constant k naught. Then the angular frequency of this spring is omega. If this spring is cut in half such that the mass is attached in between of those half springs, then the question is asking what will be the new angular frequency, omega prime, with respect to the original angular frequency. The mass attached to the spring, this is equivalent to two springs that is attached in series. And if I call these individual spring constant as k prime, then 1 over k naught should equal to 1 over k prime plus 1 over k prime equals to 2 over k prime. And therefore, k prime equals to 2 times k naught, in which when the spring is cut in half, the strength of the spring has doubled. Then analyzing the motion of the mass attached by two of these half springs, when this mass is displaced by a distance delta x, there's going to be force that is applied from the first spring, I'm going to call it F1, and there's going to be force that is exerted from the second spring, F2. And both F1 and F2 is exerted on the same direction, because for the first spring, it is going to pull the mass in order to reach equilibrium length, and the second spring is going to push the mass in order to reach the equilibrium length. And therefore, the net force, which equals to F1 plus F2, equals to 2 times k prime times delta x, in which this equals to 2 times 2 k naught times delta x equals to 4 times k naught times delta x. Therefore, the effective spring constant equals to 4 times k naught, which means omega prime, which equals to square root of k effective over the mass, equals to square root of 4 times k naught over m, which taking out the square root of 4 term, this equals to 2 times square root of k naught over m. Therefore, omega prime equals to 2 omega. The next question is question 14. In this problem, there is two types of motion. If on this T-shaped object where the rods are massless and at the end are attached objects with equal masses, then the first motion is when the bottom mass is pushed horizontally to the left, such that this T-shape is going to oscillate like this. And the second motion is that the bottom mass is given like a vertical push, such that if this is the T-shape, then only the bottom mass would oscillate like that. Now, analyzing the first motion, if I draw the force diagram, there is going to be the weight mg that is applied for all three masses, in which this force and that force is going to exert a torque that is going to cancel out. Therefore, I can safely ignore the effect of these two forces. And therefore, if the length of the rod equals L, then the torque exerted by this weight equals to negative L times mg sine theta, where theta is the angular displacement of this rod. And using small angle approximation, this is roughly equal to negative L mg theta. Now, torque equals to I alpha, and in this case, inertia equals to 3 ml squared because there exist 3 point masses that are separated by distance L from the point of rotation. And therefore, solving for alpha, alpha equals to negative L mg theta divided by 3 ml squared. And canceling off the m and the l, I get negative g over 3l theta. And therefore, period, which equals to 2 pi over the angular frequency, equals to 2 pi times square root of 3l over g. And this would be T1. Analyzing the second motion, there is the weight that is going to be applied at the bottom mass. But since these two masses are at the axis of rotation, the torque applied by the weight of these two masses are 0. Now, torque in this motion is similar to the torque in the first motion in a sense that this equals to negative L times mg sine theta. Since the arm of rotation equals L, the force is mg, and the angle equals to theta. And using small angle approximation, this equals to negative L mg theta. Now, torque equals to I alpha, and in this case, the inertia is equal to ml squared. And the reason that the inertia is ml squared instead of 3ml squared is that only this mass is rotating with respect to the axis of rotation. Now, since these two masses are located at the axis of rotation, these two masses aren't rotating. Therefore, solving for alpha, alpha equals to negative L mg theta over ml squared, which equals to negative g over L theta. Therefore, solving for period, which equals to 2 pi over the angular frequency, equals to 2 pi times square root of L over g. Since T1 was equal to 2 pi times square root of 3L over g, we can see that T2 equals to T1 divided by square root of 3, in which T1 over T2 equals the square root of 3. And the next question is question 20. In this question, there is a spring with spring constant K and equilibrium length of x naught. Now, if this spring is extended such that the total length is the double of the equilibrium length, then the length of extension equals to x naught. And therefore, the potential energy, which is given as U naught in the question, would equal to 1/2 k x naught squared. If this spring is cut into half, then this spring is equivalent to two springs that are connected in series with spring constant K prime. Now, since this spring is equivalent to two springs with half of its length with spring constant K prime connected in series, 1 over K equals to 2 over K prime, in which solving for K prime equals to 2K. If these half springs with length x naught over 2 is extended to the length of x naught, then the length of extension equals x naught over 2. And U prime, which is potential energy of this individual spring, would equal to 1/2 K prime times x naught over 2 squared, which equals to 1/2 times 2K times x naught squared over 4, in which this equals to 1 over 4 K x naught squared. Now, in the question, it says both of these half-length springs are stretched to double of its equilibrium length, which means the total potential energy is going to be 2 times the potential energy of the individual springs, in which this is going to be 1/2 k x naught squared. And we see that this potential energy equals to the original potential energy of the spring that has been stretched double of its equilibrium length. So therefore, the potential energy of two half springs equals to U naught. The next question is question 7 from 2018B. In this question, there is a box that contains a pendulum of length L. And while this pendulum is oscillating, the box is shaken upward and downward at some frequency omega. And the question is asking what should be omega in order to maximize the amplitude of oscillation. In order to solve this question, we have to approach the motion of this pendulum qualitatively. The motion of the pendulum can be divided into two, the pendulum going upward and pendulum going downward. Now, when the pendulum is going upward, this is when the box should be pushed downward, because as this goes up and as the box is moved downward, the amplitude of the motion is going to increase. Conversely speaking, when the pendulum is moving downward, this is when the box should be lifted upward, because pendulum moving downward does not affect the overall amplitude of the oscillation. Therefore, for one cycle of the pendulum, there is 2 cycles of upward motion and the downward motion, which means if omega naught is the frequency of the pendulum, 2 times omega naught would equal to omega, the frequency of the shaking, because the cycle of the shaking motion is double the frequency of the pendulum. And remember from the motion of pendulum that alpha equals to negative g over L times theta, and therefore omega naught equals the square root of g over L. Therefore, omega, which equals to 2 times omega naught, would equal to square root of 4g over L. And the final question is question 18 from 2018B. In this question, there are 2 springs that are connected in parallel, in which the first spring has spring constant K1, equilibrium length of L1, and the second spring has spring constant K2 and equilibrium length L2. And there is a force that is applied horizontally. And the question is asking, what is the effective spring constant and the effective equilibrium length? The effective spring constant is simply the sum of K1 plus K2, because these 2 springs are attached in parallel. This is because if this mass is displaced by displacement delta x, then the net force equals to the force that is applied from the first mass plus the force that is applied from the second mass, in which this can be thought as K1 times delta x plus K2 times delta x. And solving for delta x, this equals to K1 plus K2 times delta x, in which the effective spring constant is equal to the sum of the 2 spring constants. Solving for the effective equilibrium position, when L equals L effective, the net force must equal to 0. Therefore, force from the first spring and force from the second spring should add up to 0. Now, solving for F1 equals K1 times L effective minus L1. And F2 equals to K2 times L effective minus L2, because this corresponds to the delta x in Hooke's law. And this should equal to 0. And therefore, solving for L effective, I get K1 plus K2 times L effective minus K1 L1 minus K2 L2 equals 0. Therefore, L effective would be K1 L1 plus K2 L2 divided by K1 plus K2. And thus, looking at the answer, ABC has the correct effective spring constant as K equals to the sum of K1 and K2. And by looking at the equilibrium length, it looks like B is the correct answer.